Okay, so I will quickly try to cover all the topics, boost converter and buck boost converter, and we will quickly shift to the problems. We will try to see how problems can be solved. Okay, so let me start with boost converter first. As you might have seen the circuits, just for the revision's sake. In buck converter, the inductor current was the average inductor current was the average output current. Okay, in boost converter, that scenario will be changed, and here the average inductor current will be your average input current. So this is your main switch, whose duty ratio is generally given. You have the in, the not. So whatever current will flow here, that will be IL, and IL can be written as I in. IL average, rather I should say, that will. So again, the basic thing to compute the relation between output voltage to input voltage, we have to apply the volt second balance across the inductor wherever the inductor is placed. So we will first observe voltage during when switch is on across the inductor. So that would be V in only, right? Again, we are taking this kind of polarity. So VL is equal to, you can say, minus V in if you apply the KVL here, right? And during the off state of the switch,
Sir,
oh sorry, yeah, it will be V in. That's the thing you wanted to say, something?
yes, it is.
Yeah, yeah.
Yes.
And so during off state, when switch is off, you will have V in minus V naught, because during off state, this diode will be shorted and switch is anyway open. So V in. Now we can apply the average voltage across the inductor is zero, right? So V in into Dt plus V in minus V naught in 1 minus Dt can be equated to 0. Okay. I have just skipped one or two steps, so I think that should be fine because we have been doing this for a while. If you solve it V naught by V in, you will get 1 by 1 minus D. So D is nothing but the duty ratio of the switch. Let me plot the curve here. This kind of pulse would be provided, and the duration of the pulse would be, dt. Here it is t, so, and it will be repeated after every 10 seconds. If that is the case and our input is, since it is DC, so it will be constant. So let me plot the inductor voltage, and during the, you know when switch is turned on, the voltage was V in, and when switch is turned off, So inductor voltage during turn off is VL minus V in minus V naught. And since we know this is a step up chopper, so V naught is always has to be greater than V in, and here during off state is V in minus V naught, so it should be negative, right? So that's why this curve will go in the negative region. This is V in, V in. So, and after this instance, it will be repeated. And if we have drawn the waveform of inductor voltage, we can easily plot the waveform of inductor current, or that will be the slope, whether it is rising or falling. I think some assignment problems is also given based on these concepts. I think first problem it is given like how what will be the shape of your inductor current if you know the voltage across your inductor. So if you are seeing here that your V in is positive and IL, L by L to dt VIL. So if this VL is positive, your inductor current will be rising, right? Till the point it is positive, and after the point where your inductor voltage value has gone to negative region, then it will start falling. And these both slopes, the value of these both slopes might be different. Okay, that is depending on your the magnitude of the voltage. So here it is different V in minus V naught. So it will be V in minus V naught by L, the slope, and here the slope will be V in by L. Okay, so the slope might differ, and of course the period of the rising and falling is also different. But one thing will be same in the steady state. The initial value and final value will always be same after every time period. Okay, so that will not change. That will be same. The slope value might differ. The period for which it is rising or falling that might differ. But during the steady state, right? Once your circuit has reached to the steady state, your initial and final value will be same. So it will be same, and again it will rise with V in by L. Okay. So I hope it should be clear till now. If any doubt, please feel free to stop me in between.
Sir,
Yeah,
sir, this is you are talking the steady state.
yeah, I'm talking about the steady.
Yes, sir. So this is after the inductor is charged to some flux. After that point, it will be varying like this.
Yeah.
Sir, when the inductor is having zero flux,
Mm-hmm.
at that time, uh, this voltage on the positive and the negative side won't be equal, right, sir? That is on
Volt.
that is in the transient state.
Uh-huh.
Transient state, the voltage across the inductor, uh, it won't be equal. It won't be the positive values not equal to the negative area. Is it right, sir?
Uh, y- yeah, because initially it will take some time. Initially it might not be the same. You are correct. Initially it might not be the same. And even these slopes, let us suppose that it has zero initial value. Okay, so it may rise till some value, but it will decay with the same slope, even in the transient condition, right? Because it had to follow the basic, the fundamental of the properties of inductor or the KVL and KCL. These rules cannot be violated. So it will decay like that, but slowly, slowly it will rise. and at a steady state, it will pick up its initial and final value of its, during the steady state value. You got what I'm trying to say?
Yes, sir. At the transient state, the initial and final values won't be equal. When it reaches steady state, it will be equal.
Initial and final value can be initial and final value should be equal, but the magnitude that would not be the same throughout each time period. So the magnitude, let us assume this magnitude and this magnitude. This is fixed. This will be fixed during the steady state. But in
Yes.
transient, they may vary. But the initial value and final value of the voltage, current, inductor current, and inductor voltage as well, they will be equal. Okay.
Sir, if
Do
they
not
are
confuse.
equal, then flux buildup won't happen, sir.
Why?
Because flux will start from zero and then it will again come to zero after a cycle. Uh, so that because whenever we are drawing the inducted current, we are drawing that the current won't reach zero. It will always be having some DC value, inductor current,
Mhm.
uh, which means in the steady state only, the flux, whatever flux increases, is again decreasing to the same value after a cycle. Whereas
Mhm.
in transient state, uh, if the same condition exists, then the flux won't build up to that value. No, sir. It will, uh,
Yeah.
because for flux build up to happen, uh,
Mhm.
the current initially the initial and final value should not be equal. That's my understanding.
Okay. So let me rewrite what you are saying. You are saying that, let me extend to the graph on. So you are saying that
If it starts
initially
from
it will
zero,
rise,
yes,
okay?
sir, again it will reduce,
It will
but
reduce to
it will
somewhat
stop. It will
finite
stop.
value.
Yeah,
Yeah.
it will stop at some. Again, it will increase.
Again, it will rise.
This peak will be higher than the previous peak.
This peak will be higher than the previous peak.
Again, it will reduce.
It
But
will.
this should, but it will. Yes, in this way, it will rise and fall, and finally, at steady state, it will be equal.
Okay, I got your point. Yeah. So this is the manner you are trying to explain that uh, it will reach the value where it is constant after a particular moment where steady state enters, right?
Yes, sir.
Okay. But even in the transient condition, uh, you know, uh, the property of inductor, the VL into dt, right? In transient, what is happening? It is building up quickly, right? But this property should follow, right? This is the basic property of inductor. So what my understanding is, I may be wrong. What my understanding is,
Yeah, sir. This sir told. Saptarshi sir told this voltage equal to zero, integral of VL dt equal to zero, holds only in steady state.
okay, okay,
It will not be valid in transient state. That's why I'm asking.
okay. So I will have to discuss with him. I will get back to you.
Okay, sir. We can continue.
Yeah,
Sir, one more doubt, sir.
yeah, yeah. Go ahead.
If inductor is freewheeling through resistor,
Mhm.
after a certain time, it will dissipate its entire energy across the resistor, sir. The current through the inductor will become zero after a long period.
Yeah, after long period or whatever the time constant of the LR circuit, it will depend
It
on the
depends
time.
on the time constant.
Mhm.
The current through the circuit will become zero.
Yes, yes.
If it is freewheeling through a non-ideal diode, sir, it is freewheeling through non-ideal diode, then also the current will become zero.
Uh, yeah, because you see inductor as an energy source, and if it is a non-ideal diode, it will have some voltage drop across it, right?
Okay.
If some current will flow across that non-ideal diode, it will dissipate some
Wait.
energy or it will consume some energy, right?
If it is an ideal diode only, it is maintaining its current.
Yeah, if it is an ideal diode, then you can
Current
assume
will
that
not be zero.
yeah,
Current through the circuit will not be zero.
yes.
Okay. Okay.
Okay. Any other thing? Okay. So let us move ahead. So this was our inductor current waveform, and we computed, I guess, V naught by V in. Yeah, V naught by V in we computed 1 by 1 minus 3, and that you can write it as I in by I naught. Okay. If you have an ideal DC to DC converter and you are assuming no losses is occurring in the switch, okay. Okay. So this was what about ripple in inductor current? Again, we have to follow the same procedure. L del IL by dt. During turn on, what is the voltage? V in. So del IL we can write it as 3 V in by Fa. So the magnitude of ripple in current will be 3 V in by Fa. Okay. Similarly, I see we are computing here ripple in output voltage is equal to C dV by dt, and I see during on period when we observe the circuit here.
Sir,
Yeah, go ahead please.
sir, can we go with that del Q equal to C del V with that? This is same only, but
Yeah, so the thing is, you can go with that also, equal to C del V, and you can also see del Q is nothing but identity. So just let me plot the capacitor current waveform and then we will compute the
okay,
value of del Q. Then we will see what will be the difference.
okay.
I see is so you are saying that you want to proceed with this kind of thing, but this will not be the appropriate curve for this converter. Just let me write down from the circuit condition. When your switch
Yeah,
was
because of
on,
diode current.
yeah, IC is equal to minus I naught, right? Because here you are assuming I naught is going like this fashion and IC is going in this fashion. And when your switch is on, diode is disconnected and IC plus I naught is equal to IC is equal to minus I naught during on condition. During off condition, when your switch is off and diode is on, IC will be equal to I in minus. Now we have to consider these conditions and plot the graphs appropriately. Then you will see that it won't be triangular uniform like buck converter in. So IC was minus I naught, which was on, and when your switch is off, it is I in minus I naught. Since it is a boost converter, so your I in will be greater than I naught. So I hope this is fine. And now when you compute the charge stored across the capacitor, now you do not have any triangle, you have a straightforward a rectangle there, and you just need to compute the area of this rectangle that you know. But the thing is, I think some step I am missing. I in is not your DC value, right? Because I in is equal to IL.
Yes, sir. It is increasing with the.
Yeah, so you got the catch here. Do not fall for in as a constant value. In is equal to IL, and IL is it is decreasing slope. So it is better that you write IL at that point. So IL minus I naught is right. Now it would be appropriate if you would reduce not from this yet IL peak minus I naught. It will be IL peak I naught. IL peak minus I naught is no, IL peak we generally write as IL average is del IL by 2,
Plus,
right? So you can plug in those value here in the IL peak and
sir, it should be plus, right? Plus del IL bit.
oh yes, thanks. You should plug those value in IL peak and you will get the exact value when you are trying to solve any numerical. And if it is if it is uh, at the boundary of continuous and discontinuous, then only it will touch this point. Okay. Otherwise, it will have some finite value since your IL has some finite value and will look like some. Now, the charge which was discharged during the your on condition and on condition in during the on condition your inductor is getting charged, but your capacitor is getting discharged across your load. If from the circuit you can observe, right? So your capacitor is disconnected when your switch is connected, and whatever the energy has been stored by the capacitor, it will be dissipated across the load. So Hence, it is negative. We can observe from the curve that it is coming negative. And now it is more appropriate or more convenient to compute the charge from this, rectangular curve. Rectangular curve. Calculating the area of rectangular curve is anyway, it will be more convenient than computing this area of triangle plus area of rectangle. So, that's why you will get del q is equal to I naught into dt. Uh, you got the point. Del q is equal to I naught into from where
Yes,
it is.
yes.
Now we can straight away plug in here. Del q is equal to I naught into d divided by c. D d I naught by fc. Your ripple value in your output voltage. Uh, these three, four terms are generally more than enough. They are more than enough than required for any solving for solving any kind of problem. And these are also basic things. So if you know the basic voltage and current and volt second, you will get it any numerical. So if any doubt in this, discuss it. First, we will move ahead. Discontinuous conduction.
Sir,
Yeah, go ahead, please.
sir, here in the switch mode power converters, we are saying in this
Sorry.
SMPS, all these buck boost
Yes.
and all these converters, we are saying all the elements here are ideal. We are analyze at least we are using for the analysis. At least we are using the ideal elements.
Yes.
Sir, if suppose those sir can we practically realize those inductor with the minimum resistance possible? What can be the minimum resistance that the inductor can have or the
Okay.
capacitor
So for that thing, I
practically?
think these kind of problems are given in the book called Ned Mohan and Wonderland, so which I recommended. So there you will find some solved examples or even problems. There they have given appropriate value of resistances and all, and you again have to do the same thing. Just you place in the resistance here, right? So take the circuit. So basically, resistance will be introduced along in series with the inductor and series with the capacitor, right? And then you do the same analysis. You
Sir,
apply the sorry.
sorry, sir, in capacitor also will it come in series?
Yeah,
Uh,
yeah, it will be in series. Equivalent series resistance. It's term we call it.
oh, this is called ESR.
Yes, sir. Yes, yes.
Okay,
So you will find those kind of problems. You try to solve some of them. You will get better understanding regarding the practicality of the circuit.
okay, okay, sir.
So I don't think in assignment any practical circuit is.
No, no, I don't know, sir. Still not
Uh,
attempted.
okay, I have seen. I have just skimmed through. So I did not see any practical circuit, but that's why I did not take any example. Otherwise, I would have taken one or two problems from practical circuit I've discussed. But anyway, books are always there to help us.
Okay, yes, sir, you can go ahead.
So let us move ahead with discontinuous conduction. Okay, so we all know what a discontinuous conduction is. It will be there are two things you can easily identify at any point of time the behavior of the circuit, whether it is CCM or DCM. First thing, you observe the graph of inductor current, and if it is having finite amount of time related to your zero value of inductor, then you can call it discontinuous conduction mode. Otherwise, uh, as in buck converter in last session, we observed that our output voltage was not equal to the our conventional formula. Right? V naught was not equal to d by ds. It was coming as d divided by d plus v1 into vs. And the overall value during discontinuous conduction mode for the output voltage that was higher than the conventional continuous conduction mode. So that is another way to identify if you are not given with graphs and all. You can see the duty ratio. You just apply V naught is equal to K into V in, and you try to match the parameters if it is not matching. And if it is coming more than the anticipated value of the voltage, so in that case you will get to know that it is not in CCM. So
Oh, that is the way to check.
yeah, that is the way to check. So let me write it as well. First thing is, because many a times you won't be given with this condition that the circuit is in game only. So 04.9 degrees.
So then what are disadvantage that BCM mode has?
Uh, not as such, it is not disadvantageous. Only thing is that you will have to if you are not using uh, controlled kind of switches like IGBTs and MOSFETs, and if you are using ACRs, then you will have to turn it off before the completion of each time period, right? So
Mhm.
if you are using DC to DC at higher power level and you want to turn it off frequently, at least once in a time period, your switching frequency is very high, then it would be quite tedious, and that's why there are certain commutation circuits coming here, and they make the circuit even bulkier, and that is not convenient. So the only disadvantage is that you have to have a very good controlled kind of switch, uh, and advantages are there. As first advantage, you can see that your output voltage is getting beat, and another thing is that uh, what kind of parameters, what kind of degree of freedom. So if you have kind of limited value of inductor, because of course your converter is going in DCM because of a smaller value of inductance. If you give the value, if you provide the inductance higher than critical value of inductance, then it will be in CCM. So you can design with even with the lower value of inductance and appropriate tuning of the duty ratio. So you tune your duty ratio such that even with the lower inductance, you achieve the what is so called continuity of the conductor, or even you have to rely on other parameters rather than the inductance. It is very straightforward that you increase the inductance, you will get CCM, you will get lower the value of your ripple inductor current, and hence your lower value of ripple voltage. But even with lower value of inductance, because inductance and capacitance will make your circuit bulky. Generally, power electronics converters are not bulky, uh, particularly this uh, DC to DC converters. But get compact design, you will have to play with certain other parameters. Those are things. So not so called. You can directly call it drawback. I hope I am able to clear your doubt.
Yes, yes.
So other parameter was to check your V naught by V in. If it is higher than V naught by VCM, or even not equal to, then you can call it VCM. And during DCM, I will just plot IL inductor current waveform and capacitor. Now it will start from it will finish at zero. This period we know that PT period we can T12. Otherwise, for continuous conduction mode, we would have called it 1 minus D into T. So this period you have 1 minus minus 10. And whatever the value of inductor current, IL average also, that would come out to be half height, that is del IL, this D plus del by 2. So that is your average value of the inductor current. So first thing first, you compute the ratio of output to input not by V, same as similar as related to whatever you did in PCM. So PL on, this time PL on would be V in, off is, or V in minus V, to apply again volt second balance, and in VT plus E minus V naught into V1T equal to 0. So now if you will solve it, V naught by V would come out to be D1 plus D divided by out to V. So again, yours this time your transfer function of V naught by V, uh, P plus D1 is anyway less than 1. Okay, so earlier earlier it was 1 divided by 1 minus D. Now it is less than 1, and this D1 is again it is higher than 1 minus D, right? D1 is, sorry, D1 is smaller than 1 minus. I will bring back the graph and I will justify it why I am so telling you. It is also less than this, and D1 plus D is also less than. So, hmm. So both the ratio. Okay, so D1 you observe it here from the curve. This D1T is less than that 1 minus dt, right? This 1 minus dt is this. So D1T is less than 1 minus t into t. So that's what I am trying to convey. So as you 1 plus d by d1.
Sir,
Yeah, go ahead, please.
So that D1T is less than 1 minus D minus D1T, right?
Yeah, in this scenario, it is that. But what if you add this both period, 1
Ah,
minus D minus D1 plus D1, so you will get 1 minus D
okay. Oh, I
this
got it.
overall period, right?
Okay.
From this dt instant to t instant.
Ah, okay, sir.
So now it is, it could be either higher or lower. You just need to work out this, some numericals, and you observe whether it is coming or whether it is following some general trend or not. Okay. So most important, you derive this expression, and it will be different compared to our conventional one. So that's one thing. And second thing is we need the expression of d1 in terms of d, because d1 will be a known parameter. When you go and try to solve the problem, you will observe that d1 is a known parameter to you. And so how to compute d1 in terms of d, that we will see here. Okay. So
Sir, you are saying this 1 plus D by D1 is greater than 1 by 1 minus D.
no, I haven't said that. I
Okay.
just said that you go and see what is coming for you, and it is consistent or not. It may be, I am saying, it may be higher or lower.
Okay. Sir, suppose if you put in values
Mhm.
for D equal to zero point 0.5 and for D1 equal to zero point 0.3.
Yeah. So initially, what I stated that generally your this ratio V naught by V will be higher, and even in this case, you can see that uh, your numerator is also getting reduced by certain parameter, and your denominator is also getting reduced by certain parameter. Okay, but uh, here you can see this d1 will be always less than 1 minus d. So this overall thing will always be higher than the convention. So what my understanding is, it should be higher, but it might not hold true always, as I relied in the case of buck converter. So that's why I suggested that you solve some problems, and if you see those kind of relations are consistent, then it is good. And I hope it should be. And even for certain things, you can
Sir,
plug in. Yeah.
I think this becomes 1 plus D by D1 becomes less than 1 by 1 minus D only when this D1 is greater than D, I think.
Only
But,
when d1 is greater than d. Okay.
but that case will never arise.
Yeah.
So this one is 1 plus D by D1 is always greater than our conventional, our
Yes.
CCM boost.
PCM. Yeah. That should be. Yeah. Your observation is correct. That should happen. Okay then. So I was talking about to compute the d in terms of d1. So sorry, d1 in terms of d. So the thing is, we know certain parameters. We need to manipulate the expressions in certain way that we can easily extract the value of d1 in terms of d. So any approach do you think in your mind how to get d1 in terms of d, as we did in the case of a step down chopper in the last session? Anyone? uh, certain approach related to LIL, ripple current, or output current or diode current. See, you need relation between D1 and D. So you observe the circuit first. Let me bring back the circuit. So for D1 time period or during the period when your diode is conducting, that's when the D1 period is coming in action, right? So it has to do something with your diode current. And diode current can be equated to inductor current in certain sense. What is the relationship between diode current and inductor current, if you may think of?
Yeah, both are same. When it is off, when switch is off, both are same.
So how to write that expression? ID is equal to IL when switch is off,
Yes.
and that can be written as 1 minus D, right?
Ah,
In equation uh, perspective, how to write that, that is very important. And once you wrote that, um, that this expression is valid for CCM, but as you entered in the DCM mode, this 1 minus D will be changed to D1. Am I right?
yes, sir. This D is actually average of ID.
Average of ID. For D1 time, D1 into T time period, time or duration, rather, during D1 T duration, whatever the inductor current is flowing, the same current will flow through the diode. So it is just the way of writing that statement.
Hmm.
So now you know that, and you know the expression or value of IL also during this scene, right? IL was half into del IL into T plus T1, right? So this is the expression we derived,
Hmm. Yes, sir.
and we need to plug it into this expression. Okay, and del IL value you know already. It will be L del IL by dt equal to Vs. So del IL will be dVs by Fl. So just let me write it. T equal to del I T plus T1 del IL. I will tell this value dVs by Fl and 2 del plus. Can I do anything else? We have ID, but we need certain transposition in known terms. So ID, can you relate it with VS, V naught, I naught? Because IL average value you might you do not know at the moment. Why? Because for that you need to know the value of D1. But the value of D1 we are already finding. So it is not good to look in the aspect of inductor current. It's better you look in terms of I naught. So Can we say that ID average is I know
Sir, here one more D1 will come now.
where
Come right. Uh, in that ID equal to del IL by 2 into D plus D1.
D plus D1. Uh-huh. Yeah, you are correct. This D1 I follow.
Yes.
So tell me, can I write like this? ID average is equal to I naught.
Yes, sir.
Okay. So I will do that. I naught and I naught itself can be written as V naught by R. V naught by R is equal to dVs by 2. This is D plus D1.
Sir, how did
Now,
I arrive at this equation, sir? This the one written on the black in the current screen. The one
uh,
written on the black ID equal to dVs by 2FL D plus D1.
okay. Del IL value, you are fine till this step.
Uh, Sir, this half del IL to D plus D1 also.
Okay. So IL, you are okay with this? IL is equal to half into del IL into D plus D. Okay. So
No, sir.
just forget it. Let me come to this point. So here we computed IL average. IL average was half into del IL into D plus D1 into T divided by T.
You mean average? Yes, sir.
Average value, yeah.
Ah, oh,
So we
okay, okay.
concluded that IL average value was del IL by 2 into D plus D1.
Yes, sir.
Okay. So that same thing I wrote here.
Okay, okay.
Now we concluded that ID is equal to IL into D1. And I just plugged in the value
Mm,
of IL in the expression of ID. And further, I wrote ID is equal to I naught. And I naught is nothing but V naught by R. And now one more manipulation I'm going to do, and that will be V naught by Vs.
no, sir. This dVs by 2FL, how it came?
Okay, so this 2 is here. Del IL value. Del IL value is what? dVs by FL, right?
Okay, computer. Okay, sir.
So del IL value is dVs by FL. 2 was
Yeah,
already there,
yeah. You can proceed, sir.
and 1 D1 which I left.
All equations.
Now I will simplify it.
Sir, we were trying to find D in terms of D1. Na?
Yes, D1 in terms of D.
D1.
That is. So V naught by Vs I can write on one side, and other side I can write D into D plus D1 divided by 2. Well, R is here. That should be FL by R. Now V naught by Vs equal to D plus D1 by equal to into D plus 1 into R divided by FL. Now you might observe things getting simplified. So D1 is nothing but FL by R in. Is
Yes,
it
sir.
fine?
Yes, sir. Yes, sir.
I hope I haven't left any down.
So shall we solve the problem, sir?
Yes, yes. We will
Which
just,
means that that's why sir was telling you will continue with the problem.
yeah, yeah. I will just uh, go to the problems now. Just let me finish this portion. I am just verifying have I left anything. So D1, D1, one D1 was missing. Well, fine. So moving on to the problem. So which problem you are concerned with, or should I take on my own?
Yesterday sir was showing some problems. That problem he said you.
Okay. So any doubt related to current week's assignment? So just let me discuss it. So this is the problem. You read it carefully. You tell me the approach where with this. I think this is related to boost converter only. So we need to find the output voltage, the given problem,
We need to know, sir. We should know about the inductor voltage.
inductor voltage. Yeah. And in now in the expression of inductor voltage, some practicalities will be included, such as saturation voltage and the voltage drop across the diodes. And those voltages are given. So
So
let us
on state will be 4.8.
on state is 4.8 that you computed that 5 voltage minus saturation voltage.
Yes.
5 minus and 2 volt. I hope everyone else is also following. So it is 4.8 volt. And during off condition,
5 minus zero point 0.2 plus 5 minus of zero point 0.2 plus V naught.
5 minus a point, not point 2, you want to say zero point 0.7, right?
Oh, sorry. Points.
So during VL off, your 5 minus VD, that, that I need to say, and that is 5 minus zero point 0.7 and
Sir, this is
4.3.
5 minus VD plus V naught, right?
5 minus VD minus V naught. Yeah, correct. Correct. 5 minus VD minus V. So now you have voltage across the inductor during turn on and turn off. So you just need to apply the volt setting. During on condition, 4.8 volt is there, 2 dt plus during off condition minus 2 1 minus. If you solve it,
D is given.
d is given. Yeah, correct. That is point 0.4, I guess. Yeah, point 0.4. You just cancel the t, so it is common in both, plus 4.3 minus v naught, 1 minus t, that would 0.6 equal to 0. Now you have one unknown and one. It won't be a difficult task. It will be 4.8 into 0.4, 1.9. 2 plus 4.3 into 58 equal to 0.6 V naught is 2 4.5. So it is 7.5 volt. Any doubt in this problem? Okay then. So let us
Yes,
Sir,
see.
since
yes, sir. It's only
the conditions are non-ideal, we are going for this expression and solving it, not?
Yeah. We just need to take the considerations whatever
Oh,
is provided in the
oh,
problem. So
okay.
we are provided with the diode voltages and the
Saturation mode.
saturation voltages.
Okay.
So that you just need to include in the expression. So the concept is same. You just need to write the same thing VL during switch on and VL during switch off and apply the volt second balance.
And find the output voltage.
Okay then. So right. So in another problem, it has been asked that what will be the efficiency of the circuit, the same circuit, and the same data is given. Okay. So what will be the efficiency of the circuit? Uh, we observed the difference in inductor voltages, but will there be any differences in currents? Or let us rather let me write it. Efficiency nothing but V naught I naught V in I. V naught we computed 7.5 volt. V in was given 5 volt. Okay. Now the thing is I naught by I in. Okay. So we know that V naught by V equal to I naught by I in equal to 1 by 1 minus T. It is a boost condition. So
so it is I in by I naught, right?
yeah. So it will be I in by. So can we plug this value straight away to this circuit? Right,
No, sir.
7.5 with 5 to 1 minus 3. If you are saying no, then please explain why.
Sir, because we have arrived at the relation by considering the ideal elements.
Hmm.
Voltage across the BJT is zero and diode is zero when it is conducting.
Okay.
But actually, it is having some voltage now, so I think this relation will not hold.
Okay. So just let us investigate this circuit once more. See, uh, when this switch is off, okay, then only IL will be final. IL will be. The switch is off and only diode is conducting. So whatever the I that is flowing here, and this ID ID will be equal to I in 1 minus 3. Do you agree on that?
Yes, sir.
And ID average is equal to I naught average. You also agree on that. So where is the practicalities coming in the picture? It was fine for voltages because drops were there, but current is, it does not change in a series path. Whatever flowing at one node, that the same value will flow at the in the same node throughout the path. So I, I do not think it should for ID or I the relation between I and I naught will be same. Is that correct?
Okay.
Whatever
Yeah, there will be change in their values, but uh,
yes,
the
yes.
relation will still remain.
Relation will be intact. Yeah. That's what I'm trying to say. Okay. So 1 minus D, D was zero point 0.4, I guess. So 1 minus D is 0.6, 2.5, 5, 1 point. Efficiency will be 90%. Okay. Any doubt in this? Okay.
Yes, sir. You can go.
Yeah. So I am just selecting certain problems. Just go ahead with the problem. Read this problem carefully. So let me draw the circuit as well. This is a step down chopper. So this freewheeling diode term has been dedicated to this diode. Okay. And you have a load.
Sir,
Yeah. Go ahead, please.
sir, here actually we are drawing the buck converter.
Yeah, that same. That is a step down chopper. No?
So step down chopper means without this LNC component, uh, a simple DC source with a switch,
Hmm.
simple DC source with a switch,
Hmm.
then the load will be connected across at the output with no LNC and these diodes. That is called as chopper, I think. Am I
Okay.
right?
Uh, I do
This
not
is
know about that actually. Whatever step down chopper and buck converter, both terminology are just different, but both the circuits are same. That might be you might be talking about
the
class
there
A,
also step down will happen.
yeah, class A, class B. Are you referring to that? Those kind of things?
No, sir. Simple voltage source with the switch like MOSFET. Voltage source in series with the MOSFET, and then output load will be connected. Then also at the load we'll get the decreased voltage.
Okay. That you are correct. So that is nothing but the same thing. But this is also type of a step down chopper. Just the more practical way. Otherwise, very crude way of drawing the circuit is very crude way of drawing
Yes.
this. You can say that it is a step down chopper.
What is T naught?
What is T note? In the problem you are asking,
Yes, yes.
T note is the time where this uh, it is found that current is where this current will be zero. Your inductor current will be zero for that period. It means that period is nothing but 1 minus d minus d1. So indirectly you can say that discontinuous conduction mode. Just let me current increases for a time. So this period, this we identified as dt, t1t. This will be your t. Again, it will start rising and falling, and then will repeat after it. Is it fine?
Okay, sir.
So current is increases for time tr. So tr is nothing but dt, and falls to zero over tf. So this is your falling time. T naught is this
Yes, sir. From these statements, you can conclude at least it is a buck converter. The following statements: current
one.
increases. Yeah. Okay. Okay. Yeah. This statement.
So yeah, then we need to compute the average DC voltage across the freewheeling diode. Okay, so it means we are being asked about diode voltage, right? So that's why I drawn the diode here. VD, you can mark any polarity, whatever the polarity you want, you mark here. But let us assume that this is the polarity that I want to match with our load. Okay, basically. So
The output we have EB.
at the output we will have EB. So let me test this load with constant battery. So then only when the switch is off, it will be EB. Otherwise, we'll have certain other things as well. So that we will see. Well, so during on condition, your uh, inductor voltage will be equal to Vs minus EB, right? During off condition, it will be your minus V naught, that might be equal to, or that is equal to E. So from this third statement, it is sorry, the first statement, a DC motor armature with a back EMF EB. So generally, DC motor has certain resistances series. For more simplicity, we can put armature resistance in series. Okay, so armature from motor point of view, and particularly in DC motor, we represent armature is nothing but we represent this in equivalent circuit components as and a series resistance. So this is the way of representing any DC motor armature. Okay.
Sir, it
Now
is not written where the current is increasing.
it is not written where the current is increasing.
Yes.
It is written that current increases for time tr
Where?
here.
No, no, it is written, but where it is output side, input side, where?
Uh, you have oscilloscope. So what you measure? You measure the inductor current and wherever that inductor is placed, right? Or even you can measure that output side as well, but output side will be your constant since we are dealing in terms of DC to DC converter. So nothing will be variable. So if you want to see the changes in the circuit or parameters, you have to place the oscilloscope traces along the inductor. So here you in inductor we are talking about and wherever that inductor is. So in a step down chopper, we generally have inductor on the output side. On the output side, this across the inductor, your current is increasing. It's fine.
Okay, sir.
So hmm, now we can write as when because we need to find the average DC voltage across the freewheeling diode. So we need to find the voltage across freewheeling diode in every time interval. Okay, so we are considering first time interval. So from 0 to T1, that T1 is nothing but TR. This TR from 0 to DT, 0 to PR, PD is 0, right? Because, sorry, is found that for time TR, current increases means will be, transistor will be on. Transistor will be on, this VD will be equal to, so it will be VS. Any doubt in this? VD will be equal to VS. When the switch off and that period is TR. Okay. Now, when the switch is off, when current is falling for this period, VD will be equal to SVD plus VL plus, so during that period, this is your KVL equation. But for applying the KVL, you should think that when this diode is conducting, and we have to assume ideal until it has mentioned should be zero, right? because it is conducting. Voltage across diode will be zero for that period. So this fall time TF during TF, VD will be equal to 0. Yeah, okay. The final interval is TF to T naught. Here, the inductor current is 0. It means this inductor current is 0. No drop across the resistor. So whatever the VD, whatever the back EMF is there, that will be equal to VD. VD will be equal to EF to
T naught.
EF plus T is equal to EV. Now we need to find out the average value of this diode.
Vs into TR.
Correct. So Vs into PR, VD average.
Sir, when there is no current flowing, then VD is going to be zero. VD is zero.
VD
No
will
inductor
be,
current.
yeah, when no inductor current is flowing, then this EV is in parallel with this VD, right?
Okay.
And in parallel, whatever the voltage will be there, that will reflect directly to the nodes.
Okay,
Is
sir.
it fine? So
Sir, sir,
yeah,
adding to
go.
this doubt, same doubt, uh, during T naught period,
Mhm.
anode is connected at negative terminal, and the cathode is and the inductor is an open circuit, and the anode is at the free position, no, where it is connected, sir, to see its
Uh,
open circuit voltage.
Open circuit voltage of diode you are asking?
Yes, sir.
Okay. So you are saying that this inductor is open.
Yes, sir. It is not
How?
conducting.
No, not conducting will not imply to it will be zero, right?
Yeah.
See, during discontinuous conduction mode, there is this period comes. Okay, so it doesn't mean that it is open. You cannot say that it is cap. If it would have been a capacitor, then you could have called that yeah, it is open. But inductor is not treated in that way. Okay,
Okay, sir.
so VD average we were calculating, so it is Vs into TR plus 0 into TF plus EB into
T naught.
T naught divided by PR plus TF plus T naught. So this is your answer of the problem. Okay. Any final doubt in this problem?
Sir, in this problem, I think that instead of current, they would have specified the inductor current.
They should have. They should have, but still, you need to something play with. So you
Yeah, if it is an
other,
assignment, it's okay. But if in the exam,
uh,
if something comes like this, we will be wasting the time.
yeah, but there are no other elements which increases or decreases. Current flow which increases or decreases. So you can pick from that point only. That which current is increasing. Or rather, even capacitor current also that could be increasing or decreasing. it is not particularly clear. I agree on that.
So voltage drop across RE.
Voltage across drop across RA, we are taking that V naught is equal to I naught RA plus EB, right? But since we directly took the value of V naught, right? We dealt in terms of V naught. We did not bother about RA as we took the V naught directly. But during the off condition, if some current would have flown through the RA, but that is not the case, then V naught could have been equal to IARA plus EB, right?
Okay, sir.
So one basic problem based on power loss. So yeah, so first we will draw the plot of the function that 1 by 1 minus d, that transfer function that we discussed earlier. Please excuse me for 2 minutes. I will just come back. Yeah, so I am back. Anyone able to draw the waveform of this function?
It will it will start at 1. F of d will be 1 at the start.
Right, right. Will because initially it will be the dt will be zero, right? We need to plot d, right? F of d. And d is 0, 1 by 1 minus 1 will be 1. And when d will be 1, then it would go to infinite. Okay? So This is the characteristics of the circuit, but it will not happen in the practical circuit because there you will have some finite resistances and you will observe that some resistances will be added in denominator. This kind of in practical circuit it happens
Resistance
like
you
this.
mean diode resistance?
Sorry. No,
Resistance.
not diode resistance. I am talking about inductor resistance and EHR, coil resistance. So this is the characteristic of practical, not like this. You may find in textbook. So was all, and one more problem could be added that in this problem, average. This is the statement of another problem. Average current is given, right? So if average current is given, you know what is given. That is yours. Average input current if you are given with average.
So the question 9 is this previous one we discussed.
Yeah. This was question 9, and this is question 10 of previous year assignment. So IL1 is 5 ampere current flow inductor for an output voltage of 20. So output voltage is also given 24 volt and power delivered to the resistor RL that you need to compute. If but if
Yes,
output
product there.
voltage is given, then what is there to? Yeah, you are not given with RL, right? That was the requirement, the problem. So V naught can be equal to V naught I naught could be equal to V9 since had been explicitly mentioned that your converter is lossless.
Sir,
Yeah, go ahead, please.
sir, they are asking power delivered to RL, but RL is not needed here, right? Just the product of 24 into 5 is will be sufficient.
24 into 5 would not be sufficient because IL1 is not your output current, right? So
IL,
24
IL average, right?
IL average is also not your output current.
Yes, sir.
Oh, okay.
Your output current is diode current, and ID average will be equal to IL
In
average.
average.
Yeah, understood, sir. We can go, sir.
Yeah, yeah. So I not average, ID average equal to IL into 1 minus D. 1 minus D is 0.4, D is given 0.6.4, and average is given 5, so it will be 12. Yeah. V naught is V naught I naught, and V naught is 4, and I naught is 248 volt once. Okay.
Sir,
Yeah, go ahead, please.
uh, previous example, we have calculated that average voltage across the diode,
Right. Yeah.
and that is for fall fall time. We have taken 0 across
Zero.
the diode,
Yes.
and EB the back EMF into T0.
Yes.
So current through VD, current through diode is not 0, but drop across the diode is 0.
Current through diode is non-zero. Yeah, because it is an ideal diode, no? So when any switch is on or diode is on, E is equal to 0, I can be finite. No?
Okay.
this was all related to previous year's assignment. If any doubt related to current year's assignment, we can discuss it. Otherwise, we will find out the problem.
Sir,
Yeah, go ahead, please.
sir, regarding the assignment we discussed earlier, the case of assignment number 4 for capacitor calculation, the solution manual was slightly different from what we have calculated. Sir.
For assignment 4, you are talking.
Yes, sir. We have used a different expression in the class for calculating
But
capacitance.
answer is
Right.
varying or is it same? Varying.
Sir, can you hear, sir?
Yeah, I can hear you. You are saying that in assignment 4, whole question, right?
Yes, sir. The case of third question, calculating the value of C.
Hmm. ICRMS. Okay. So how did you compute this value?
Sir, one second, one second. I'll take my.
Uh,
Can you
but
go
you,
up a little bit? This slide.
okay, no, this slide,
Oh,
yeah.
this. Okay.
The value of capacitance is calculated by the discharging equation.
Discharging expression, right?
Yes, we used that, but here some other have taken the page.
No, from the you took V is equal to Vm into e raised to power minus t by tau.
Three different expressions here.
Really, I haven't seen the solution. Where to find the solution of this assignment?
Sir,
Sir, which problem, sir?
See, talking about
assignment.
quiz 4,
ते pen drive दे
Third problem here for a capacitor calculation.
third problem, minimum capacitor value for this region specification. If you could please share your screen, then it would be more convenient. Is it possible for you?
I don't know, sir. Whether screen, share screen is possible. Let me check.
So related to current week's assignment, you do not have any doubts, right? So I think we are fine with discussing.
sir.
Yeah.
I have doubt about first question of week 7 assignment.
Okay. So meanwhile, you search for that.
You don't find the solution manual, sir?
Actually, I do not get where to select this.
Okay, let me check to scan.
So the this question, yes sir.
See, we need to identify the characteristics of load current. So the first thing, and if the switch is flowed for this period, 0 to 100 microseconds, and then open. So this switch is flowed for 100 microseconds. First, we will observe the inductor current heavier for this period, and after that, when the switch is open, then we will again observe. So you see, when the switch is closed, the circuit will have something like this. This diode will be forward biased, this diode will be reverse biased. Agree?
Yes, yes.
And your inductor will be charged.
Charge.
Yeah. And the slope of inductor will be 100 by L. Okay.
100 by L. Yes, 100 by L.
So it will charge from 0 to,
Yeah, 100 by L into dt will be the delta I.
yeah. So D is anyway, it is given. You do not need to compute D because P on is given directly.
Huh, 100 microseconds
100 micros.
into
And this
100
is
volt divided by.
the Vs by L.
Hmm.
L is also given. So you can identify the slope till 100 microseconds.
It is 50 ampere.
It is 50 ampere, 100 by 200. Yeah. 50 ampere. Yeah.
So delta I is equal to 50 ampere.
Delta I is equal to 50 ampere. Yeah. And
And
after that, yeah, go ahead, please.
then the current is going to circulate for the infinite time, same current 50 ampere.
Same current because you do
Because
not
it is
have
not having any path other than the diode.
any lossy current. So your slope will be then again,
A straight line,
yeah, because it will be constant.
constant. So it will be C.
Sorry. If you see, if you draw the equivalent during off period, you will see like this, right?
Okay.
And your VL is zero. Now,
VL is 0.
yeah, because you have short circuit.
No, we have
So you,
open circuited, na sir. This is the VL is 0 due to diode.
due to diode, VL is zero because VL is now short circuited, and voltage across any short circuit wire is zero, right? So this energy will be circulated across this diode.
With diode, yes.
Yeah,
But
and
that amount of circulating current is 50 ampere.
the same because whatever the slope you can compute from here, if your VL is zero, your dropping slope will be equal to VL by L, right? And VL is zero, so your slope is zero. So you identify from
So it is VL is 0.
that. You got the point why VL is, I am saying zero.
No, 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 sir.
Okay. See, when this switch will be turned off, okay, and
Okay.
this current, this inductor was earlier, it was passive device, right?
Yes.
Earlier it was absorbing the energy.
Hmm.
Now, when it does not have any source to deliver to the inductor, now it will dissipate its energy. And when some element becomes active,
Okay.
it will be in this fashion.
Okay.
And your diode is your diode will be forward biased and your current will flow like this, and your energy will be flowing or current will be circulating through the diode, and since there are no lossy components, so current will be same. And what I mean by no lossy components, this voltage won't be getting dropped across it there, right? So this node, if you see, there are no voltage if this diode has been short circuited,
Hmm.
right? So if this diode has been short circuited, you have VL is equal to, you can say, right, from KVL, VL is equal to zero.
VL is equal to 0.
You can say that, right?
Yes.
So if you can say that, now your IL or slope, right? Rather, VL by L, the slope is only changing here.
Hmm.
So now slope is 0 here, del IL into dt.
VL into dt divided by L is equal to 0.
Yeah. And
So,
what does it mean? If your slope is 0, it does mean that it will be flat.
it is flat. Yes. Then the yes, yes. Okay, okay, got it. Slope is 0. Okay, okay. Slope is 0 means it's flat. Okay, okay, fine.
It
Okay, got
doesn't mean that slope is 0, then you
Okay,
will.
okay, okay. Got it, got it. So infinitely the current is going to circulate through diode and inductor.
Yeah, that's correct.
Okay, thank you, sir.
It is saying I need access. The Dakshina, I am not able to access that file, that jam file, because I need access. Uh, Could you explain in crude words like what are the deviation? Because I am able to see the problem, just I am not able to see the solution. So could you explain what
Paste
are
the
the, sorry?
1 second.
Yes. Or even if you are able to share your screen, that would be perfect.
Sir, what is this link for?
Uh, she has shared the link for the solution of week four assignment.
Week 4 assignment was shared to all. Assignment solution is shared to all.
I
Let me share the link. Then you in the chat. Then you can access. I think.
okay.
Then what is this link for?
This link is for she saying that she has shared some solution of that question number three. Is it right, Pradakshina?
No, sir. It was done and sent to all. So the final answer was shared to all. But what we have discussed and given and what is given in the solution manual is slightly different. Sir. So the answer I got was different. So
So
want to know.
how they solved that problem? Do you have any?
Did you see that
एक
link in the chat?
I saw the you now shared right. That is very good.
Yeah, now you can.
Yeah, thank you. Third problem is capacity.
How the expression for C is derived as well.
Sir,
Yeah, yeah, go ahead.
sir, like it is said, the question is eliminated due to insufficient data.
Okay, so if this is eliminated, then it should not be any issue, right?
Then that expression, how does it arrive? That is the question, sir. We did it the other way. What is given in this?
So VM1 is okay. So I will see this solution and I will try to extract
Okay.
the information what is given.
Okay. Similarly for the capacitor RMS current also, sir.
Capacitor RMS current. That question number four, right?
Yes, sir. We
Okay.
did, we did through in terms of sin omega t and cos omega t, and
Okay.
integrated for finding the RMS current, and it is given the different ways.
So, the way by which you did you get answer in the range or outside
No,
of the
so the
range?
answer was wrong. That is the problem.
Okay. So I will see this third and fourth problem.
Okay, sir.
In
And
next
what's the
session, we can.
how to arrive at expression?
Yeah, sure. Okay. So
Thank
I
you.
think thank you. Yeah. So we are done with this week's session. The final thing what we are stuck at in the last week. So I am going to explain that thing once more. And I think indirectly I discussed in the last problem, but let's see again. Rahul was there. Okay. Anyway, he is not here, but anyway, I will discuss it and Gordon will be there. So he asked that why this voltage not being created. Just let me draw this circuit for the buck converter. And I think indirectly I just answered this problem. So this is your VL. So when this switch was on and this diode was off, your inductor was charging and inductor is acting as a passive device. So VL polarity would be like this, right? And for IN equal to IA. So if this kind of polarity is there, this node will be plus and this diode will be off. Okay. Now during off condition, oh sorry, the other when the switch is off, now this inductor has to supply the energy to resistance, right? And whenever any element that supply its energy, that becomes active energy and the notation of polarity changes. As we discussed in the last problem, it will be reversed, right? So now it can supply the current to your capacitor, your load, and your diode will see this negative across its cathode and it will become forward bias. So I hope it should answer his question or anyone who has in the mind. So I think that's all about that minute thing. But yeah, it's better to clarify our concepts so that nuances should be eliminated. Is it fine with everyone?
You mean to say current is falling now?
Current is falling, and
Falling.
when current is falling through the inductor, it means it is discharging. And when it is discharging, we study in transient analysis of circuit that when inductor discharges, it means it has become the active element now. And whenever any active elements are there, since resistors are considered as passive elements, so its drop we denote it like that. Okay. And if any voltage source is there connected to that element, so current is entering from the negative polarity. And if any passive element is there, current will enter at positive polarity. So that was very basic from circuit theory. So that's the all funda we can apply everywhere. Is it fine?
Yes, sir. This session will be in the YouTube.
Yeah, within half an hour it will be.
Okay. with audio.
with audio. Yeah.
Last
Uh,
2 3 sessions,
last session was not audible.
no, some sessions of other people have not there with audio.
Okay, but I make sure that audio is there during recording. So I do not think my any video has no audio.
Sir,
With au-
Sir, even the last session has not having
let's
audio.
take the one issue here, sir.
yeah, yeah, go ahead, please.
If this switches off for infinite time,
Uh,
now what will happen, sir? This current will be transferring between the energy is being transferred from inductor to capacitor, or what would be happening?
um, uh, the first statement, could you please repeat that?
If the
You said
switch is off or the switch is on, turned on, and the inductor is charged, and the voltage across the capacitor, voltage across the capacitor is V naught, and
so.
after a period of time, the switch is turned off.
Okay.
If the switch is turned off for infinite period of time,
Mhm.
what would happen?
If switch is turned off for infinite period of time, first of all, the amount of time it will require to dissipate its energy through the resistance, uh, in that time it will be discharged and your current will be zero. But if there is no load, suppose you have only L and C kind of thing,
Yes,
you have,
here C is also fully charged.
and your inductor is fully charged. So
Yes,
this condition is called a resonant condition, and the frequency of oscillation, your current will oscillate with the frequency of 1 by under root LC,
2 pi root L.
and it will keep oscillating, right? So your
Okay,
capacitor will be charged, then it will discharge across the inductor, and the same thing will happen repeatedly.
okay.
So this condition is known as resonant condition.
This was discussed earlier in
In one session, I
before
might
three.
discuss.
Yes, we have discussed this one.
Yes.
Here the capacitor is fully charged condition,
Uh,
and in that case where the capacitor would be charging after some time, it would be remain still no, sir. What is an action of capacitor here then?
you are saying when this capacitor is charged,
This case it's also fully charged.
fully charged, and your inductor is also fully charged.
Yes.
That's what
What
you
is
are
the
saying.
reaction here, sir?
Okay. So now your if it is a fully charged, then what happens? Your inductor become current source of the capacitor becomes open open circuit with voltage VC. So now your inductor has become the current source, but it is seeing the open path. It is not seeing any path to flow, right? So, you know, in that case, we are exceeding the capacitor limit, right? So, in that case, capacitor might get damaged because your inductor, it is quite rugged kind of thing, but capacitor is what it is charged. And you can say that why not inductor is getting damaged? That should be the valid question. But here inductor, whatever the current is flowing, you cannot accumulate further. But whatever the voltage is there, that will be become VC is equal to VC zero plus C DIL by dt. Okay. So this DIL term is positive, right? So DIL by dt, it will be increasing and it will try to increase. So if you are trying to violate the capacitor limit, it might damage the capacitor first. So initially what? Your capacitor will be at the higher current to get damaged.
Here we have a load. Suppose the load is also open circuited and this will hold. Here we have a load connected across C node, sir.
Here in parallel or series?
Parallel with the C. This
Parallel with
C.
yeah. Yeah.
So no problem. If suppose the load is also open circuited, we will end up in such a case.
Yeah, we
Right?
will end up in such case. Okay, so load has been opened. So what was your question again in this case?
It's the same thing, sir. If the load is if the load is there, we can say the current would be circulating in the path. If the load is also open circuited, after an
Huh.
infinite time, what would happen?
Load will be opened after infinite time. Of
See, the
which
switch is also open for infinite time, and this load side is also open.
huh,
In such situation, what is then current through this LNC circuit?
I guess it will be same if even if load is there and load is disconnected, then we are treating it as a LC circuit again.
Yes, sir.
Same thing will happen.
So the same current will be circulating in the circuit.
Yeah, same current will be circulating that with frequency of you know and resonant frequency. With this frequency, current will circulate. Did I answer your question, or is there some ambiguity, or am I not able to get your question properly? You are muted.
It's once.
Okay, then
Okay,
so
sir. Okay.
okay, so in next session I will see those third and fourth problem where is the discrepancy. We will carry on with uh, further more circuits of DC to DC converters such as flyback and forward converter. So they are kind of more practical converters because they are isolated as well. And with conductive DC to DC converters, we couldn't have the duty ratio of even close to two. We cannot have the duty ratio of two, but with isolated DC-DC converters, we can go up to three, four, or even 10. So, since it has the luxury of transformer, with what I mean by luxury of transformer, it will be inductive circuit. It will not be any more conductive circuit. So you can play with that circuit. So that's all uh, about today's session. I think we can end it here. If any other final question, I am ready to take. Otherwise, we will wind it up.
Okay, thank you, sir.
Thank you. Thank you.
Thank you,
Okay, sir.
sir.
Thank you, sir.
Thank you.
Bye.
Thank you very much.